Hi, everyone, and welcome to another episode of Training_Data. I know it's been a long hiatus, and I can just sense a sigh of relief across the internet community that we are back. In similar protocol to previous episodes, we're still practicing social distancing, but we'll be doing this virtually. And so today we're going to be returning to one of our most favorite topics, which is SpaceNet, and specifically our most recently concluded challenge, SpaceNet 6. If you listened to our previous episode on this, where we were introducing the challenge before it launched back in March, we referred to the development and release of a co-registered electro-optical and synthetic aperture radar data set as our white whale. And I believe we had nominated Jake to be our Captain Ahab. Well, Captain Ahab is back, as well as other characters, which we can get into today. And I think one of the reasons that we were so excited about SpaceNet 6 and we consider it sort of this long-sought challenge is because it represents something truly unique, not just for the SpaceNet community, but for computer vision applied research more broadly. And so if you haven't listened before, SpaceNet, it's a nonprofit organization. It's managed by us here at CosmiQ in close collaboration with our co-chair, Maxar Technologies, and then all of our other SpaceNet partners, which is Amazon Web Services, Intel AI, Capella Space, Topcoder, the IEEE GRSS, NGA, and now Planet. And specifically, what we'll be talking about today in our sixth challenge is really the structure of the challenge, which we covered a little bit in our past episode, but more specifically getting into when the challenge ran, what prizes were offered, and the most exciting part, which was who won and what has been some of the findings and research that have come out of this challenge. So we'll get into all that today. Along with me is the one and only Captain Ahab, which is sometimes some people know him as Jake Shermeyer. It just depends who you talk to. Jake, welcome back to the show.
Hey, great to be back, Ryan. Yeah, I think we can safely say mission accomplished. We've slain the whale, harpooned it, if you will, with SAR beams, perhaps, and we actually survived, which is also an exciting bonus. So great to be back on Training Data.
Yeah, it's an alternative ending, like a choose your own adventure. And also, it's great to have him back on the show, Daniel Hogan. Daniel, welcome.
Hi, great to be back.
I don't know what character you represent in Moby Dick, but at the end of this podcast, I would like you to select a character, please.
Very good.
All right, excellent. I won't forget. All right, so let's get into really the most into the details right away. Right, we talked a little bit about this in previous episode, but as a reminder, Jake, why don't you just jump into an overview of the data set and a little bit about why that's unique, and then we can get into some of the more specifics of the challenge.
Yeah, sure. So the data set was really unique. It was, as we said, the first data set that contained both optical and SAR imagery co-registered over a single location. So the location in this setting was Rotterdam, the Netherlands. And our SAR data came from Capella Space with the optical data from Maxar. So the data set was actually captured in August. Capella flew an aerial flight. So this is, they're about to launch their first satellite. They have this new sensor. They want to test out how well it performs before they actually put it in space. So that's why they created this data set, mounted it on this aerial sensor. They ended up capturing 204 image strips over Rotterdam over a 3-day time span. Our optical data in this case came from the Maxar Worldview 2 satellite. So we have a single shot here just about a week after the Capella data was captured. And both of these are about a half-meter spatial resolution. The task for SpaceNet 6 was extracting building footprints automatically using a combination of these data sets. And for our labels here, we use an existing data set called 3D Bag, which spans the entirety of the Netherlands. We crop it down to Rotterdam. And another interesting aspect of this data set is that it has actually height information associated with it. So that enables us to pull out some interesting primer or points, so we can investigate actually how height influences the ability to detect buildings with SAR data. So yeah, a lot of interesting aspects here. The participation in the challenge was awesome, and we're excited to share a lot of this today.
Yeah, and for those of you that may not be as familiar or maybe not familiar at all with the remote sensing industry or just geospatial data sets more generally, is SAR is a data set that's often discussed, and but it's rare that it is diffusely data sets are diffusely distributed. It's kind of known as being hard to get, and as a result of those barriers to entry, only certain groups really provide research. So I think as a broader context, what Jake's saying, it was really exciting for us to put this out in a much more open manner, because we think it will hopefully jumpstart additional research in looking at deep learning on synthetic aperture radar data sets. There is a lot of difference, certainly between electro-optical or passive collect and an active collect like SAR. And those should not be overlooked when we're thinking about how machine learning models are applied, or perhaps how they don't translate across the two different modalities. Daniel, why don't you walk us through at the high level some of the advantages of SAR, but then more specifically some of the technical challenges that an active collect presents relative to just an image, which is intuitively a lot easier to understand.
Yeah, so the idea with SAR, synthetic aperture radar, is that you're taking a picture of the ground using a radar instrument that's mounted on a moving airplane or a satellite, and actually the technology takes advantage of that motion to get higher resolution than would otherwise be possible. The main advantage of this approach is that because you are providing the illumination with the radar pulses, you can do this at night. You can even do it on a cloudy day, because at the right frequencies, radar doesn't care about that. And there are disadvantages as well, one being that the images have some distortions that are a little tricky to think about. With this approach, one figures out the distance to things by the amount of time for the radar echoes to return to the sensor. And so, for example, if you have a skyscraper, the echo from the top of the skyscraper will actually get back before the echo from the bottom of the skyscraper. And so that leads to a kind of distorted picture where the building even appears to be kind of laid out horizontally due to the distortion. The flip side of that is that there are also advantages to this different approach. One being that you can use different kinds of radar pulses. You can polarize the beam in different ways. And based on the difference in the strength of the echo you get back, and even offsets of the echo in terms of frequency, or in terms of phase, excuse me, you can learn more information about the structure of what's there on the ground. So you lose some information relative to a normal photograph, but you also gain some information.
And with all that in mind, then, what does that mean in terms of how we went about structuring the challenge? Because given those differences that you're highlighting, we have to take that in consideration when we're thinking about what type of technical challenge we're going to pose to competitors, and also how we even structure which data are used for training and which data we hold back maybe for testing. Could you talk a little bit about that, Daniel?
Yeah, that's right. So for this challenge, for the training data, challenge participants were given SAR data and optical data, that is to say normal photographs from satellites, for the same geographic locations to use for training their models. Then when it came time to test the models, to ask them to run inference on previously unseen data, for that they were only given SAR. And the reason to do that was to simulate a real-world situation where you might have a lot of historical data in different modalities, but then something happens like a natural disaster where you need new imagery immediately, and maybe it's just cloudy that week and SAR is the only thing you can get.
Well, that's outstanding. And so with all that in mind, let's talk about, one thing that we've discussed a lot in previous episodes is that for each SpaceNet challenge, we always want to try to help participants, particularly those perhaps not familiar with geo, get a jump start. With all this that you're just discussing around the data set, the challenge structure, could you talk a little bit about the algorithmic baseline, Daniel, that you put together and open sourced, really as a starting point for competitors to get going in the challenge?
Yeah, that's exactly right. So we want to always lower the barrier to entry to make it easier for new people with different backgrounds and different skill sets to come in and do this kind of work. And one of the many ways that we do that for these SpaceNet challenges is, as you said, create an algorithmic baseline, which is a complete working example solution to the challenge that challenge participants are being asked to do. And so the algorithmic baseline for this challenge used a UNet architecture for a deep learning model with a VGG11 encoder. And it also, to take advantage of the optical data, used a transfer learning approach where the model was initially trained on the optical data to learn some of the basics of finding things in overhead imagery. And then it was trained again on the SAR data to specifically gain expertise in the problem that it was being asked to solve.
And how did, for those who haven't read your blog post, how did the initial baseline model do?
So the initial baseline model is mediocre. The way that we evaluate model performance is with a very elegant metric that we call the SpaceNet metric. The way it works is that for every predicted building footprint coming out of the model, if it has an intersection over union with an actual ground truth building footprint in excess of 1/2, then we call it correct. And the F1 score for correct footprint predictions is then calculated. The reason why this is a nice metric to use is that it penalizes the right sorts of things. If a prediction just gets the location of the walls a little bit wrong, that's not penalized. But if it misses a building entirely or fabricates a building out of nothing, then that definitely is. So by that metric, the baseline came in with a score in the neighborhood of a 0.21 F1 score, call it 21 points or something. But as we'll see, some of the competitors achieved scores well in excess of that, which was pretty exciting to see.
Yeah, absolutely. Well, why don't we take a quick break, and then when we come back, we'll dive into the most interesting part, which is how well the competitors did, especially relative to our baseline, and then most interestingly, how did they do it? So we'll be back in a short second. All right, we're back with Jake Shermeyer and Daniel Hogan talking about the long-awaited results from the SpaceNet 6 challenge. Before the break, we were talking about the algorithmic baseline that we put together and how the results, not surprisingly, were, as Daniel put it, mediocre. But I think what was really compelling, and Jake kind of insinuated this, is we had really strong results. And so, Jake, if you could just a little bit give an overview of just how competitive was this challenge? Where were some of the competitors coming from? And then from that, let's get into the top 5 and how they did so well.
Yeah, so I mean, this was definitely the most competitive SpaceNet challenge to date. We had over 1,600 unique submissions, so that's a lot of code, a lot of GPU hours crunching here. We had over 400 registrants for the challenge as well, so it was a really great participation metrics here. Some of the best really computer vision scientists in the world, and I'll talk a little bit about that in a minute. But the challenge ran for a few months, well, 6 weeks, as we said, and ended up handing out over $50,000 in cash prizes, as well as 15,000 in AWS GPU credits to get people spun up and started on this. So without further ado, our top 5 here, the competition was won by Zbigniew Wojna. Now that's a very Polish name, certainly saying that wrong. I've affectionately referred to him as Woj from this point forward. So when you hear me say Woj, I'm talking about the winner. In second place, we had Maximov KA. And third was the SatShip AI team. Fourth, Moto Kimura. And fifth was Selim Stuff. Now, some of these people are returning champions or returning winners, specifically Maximov and Selim Stuff. They've both placed in prior SpaceNet competitions. Zbigniew Wojna, or Woj, was the winner, as I said, and he is the CTO, I believe, for a startup company called TensorFlight in Poland that specializes in computer vision applications for overhead imagery. And also the SatShip AI team is another startup based in Greece, and they actually specialize in overhead imagery work as well. So the challenge was really cool. The winning margin here was 2.4 points. The winning score was 42.4. Now 2.4 points might not sound like a lot, but that's actually the second largest margin of victory in the history of all of our 6 SpaceNet challenges, which was interesting to see. Now, the largest margin of victory came in SpaceNet 2, which was won by XDXD, and he won by 5 points. And he did that with an ensemble of deep learning models. And this was the first time in the challenge series that was introduced. And since then, that's been the standard approach ever since then, which is really interesting. Another interesting aspect about the challenge was really how prevalent some of these newer approaches were in the computer vision space. So we're talking about the newest and best deep learning networks are really being applied here. Specifically EfficientNet. So EfficientNet was just developed. It set the benchmark for ImageNet classification, and people use this as part of their neural networks. EfficientNet is, although it set this benchmark, it's actually faster and smaller than any other network in its class so ever set this benchmark. And it was actually created with an auto ML approach. So this means they actually used another network to design this network to create it in a way that it can be heavily optimized for both speed and performance. So yeah, a lot of interesting things.
To jump in on that point just for a sec, just because it's, as we approach our 4-year anniversary for SpaceNet, it is rather astounding just in that short time span to see not only the incorporation of deep learning, but more specifically how efficient, or I should say optimized, some of these models have become relative to our early submissions. And it's something that, to be quite honest with you, I was really surprised to see the results come out of from the competitors using EfficientNet.
Yeah, it's cool, and it actually shows how we're really advancing towards actually having this be real world relevant. Because originally you would have to train these networks for days on days to get them to peak in performance, and then inference time would be really slow. It would take hours to make predictions over several square kilometers. Now we're seeing performance where we gave competitors 7 days to train their models. They only took 2. That was the longest training time, which is really cool. And the winner actually had the fastest algorithm as well, which was interesting. So when we go to inference time, I believe it's about 5 seconds per square kilometer. So that's actually pretty quick in terms of being able to create predictions and outputs in near real time.
And so, we've seen certainly large performance increases on the model side, but I'm curious, from the performance perspective, where did you see the models really do well, and then alternatively, where did you see them really struggle in terms of, i.e., where is there still work to do? There's always work to do in this domain. Where should future development be focused if it's going to stay on this application of building footprint detection?
Yeah, I mean, So, I mean, I think there's one challenge that kind of goes to both optical data and SAR data. So, I mean, although this is a SAR-focused challenge, models trained on optical data still struggle with this. And this is really finding tiny objects that are really only a couple pixels in size. So when we look at building footprints that are really under about 30 meters squared, they're generally undetectable, even by these best-in-class, state-of-the-art computer vision algorithms. Another aspect that I think really could warrant some more development is, and something that we touched on in SpaceNet 4, is the off-nadir perspective. And this is a challenge we see in both optical and in SAR data. When you're imaging from an oblique look angle, that causes further distortions. It causes, it contributes to these layover effects Daniel was discussing earlier about how the top of the building echoes back more quickly. And in optical imagery, it causes the buildings to lean or tilt. And what that does is it causes offsets in your model's predictions, and the computer vision algorithms really can't comprehend how to shift their predictions away from just detecting buildings to detecting the base of the buildings, which is what we're interested in, finding the footprints of where these structures actually are. So I think further advancement in research really is required in those two areas.
Yeah, so as work's going down down that path, it's worth sort of exploring, how do these results compare to just the standalone electro-optical, i.e., like, are they similar or were they different?
Yeah, so we actually, so although the competitors only really had access to SAR data during inference time, we at SpaceNet, we have this optical data. So we ended up retraining the winner, Woj's algorithm, to do a building footprint extraction with optical data only, and then we test with that optical data as well, just to see the performance differences. So he had a score of about a 42.4 with the SAR data. When we look at the optical data, that goes up to a score of around 69. So that's a nice performance boost. So what is the real differences here? What's missing, or what explains these performance differences? So with optical imagery, you're definitely able to detect structures that are smaller than you are with SAR data. And part of that really, I think, deals with color. So the SAR imagery, it's really all about measuring that backscatter, what's being shot to the ground, it's echoing back to the sensor in some way. With optical data, you actually have color, so you can see differences between vegetation and differences between buildings, and that's certainly helpful. Another interesting fact here that we saw, and we talked about this a little bit, was the layover. So with tall buildings, we actually saw a decreased performance with SAR data due to this noise coming back off of the sensor. And you don't have that problem with optical data. Taller buildings are not really as influenced as much as they are with SAR data.
And so, as we look ahead, for future work that just we're thinking about, well, I'll start with you, Jake. Like, what are some things that are in the front of your mind about stuff that you want to be working on in terms of either leveraging this data set, or as you're highlighting, just leveraging some of the findings that we've had from the models to date?
Yeah, I mean, I think the first thing that comes to mind is really colorization. So finding some way to use the optical data to pre-process your SAR. So only 2 of the top 5 ended up using the optical data in any way during their training. They pre-trained on optical data for all or a portion of their networks. But the winner actually, and 3 of the top 5 just pre-trained on ImageNet. So this is a totally different modality. We were surprised by this. We really thought that training on optical data from the overhead perspective would really be helpful for these models. But the way we've structured the data set, it still enables people to do cool things. So there's a process called colorization. So can we steal some of the color from the optical image, train a network to find that, and then colorize our SAR data in some way, and then use that as a pre-processing step when you don't have optical data available. So we're starting to run some experiments on that, hopefully have results out here on that in about a month, which is really exciting. Another aspect here that I think is interesting is moving towards real foundational mapping. So what do I mean by that? We're talking about mapping things. So we score each individual tile in SpaceNet. So we're just really calculating the scores of tiles. But what that does is it actually magnifies things like edge effects. So when a building's cropped in half, those sorts of things. So what we were planning to do was really evaluate performance on a city scale. So we want to stitch all these predictions back together and then see how well performance actually is in a real setting. So we're not isolating down to tiles where you might have some complications. How well does this actually do at broad scale? And some of our past projects have touched on this too, like Adam's work with roads. Yeah, so I think those are some of the most interesting aspects worth exploring.
Yeah, and particularly in the second part, Jake, just understanding the utility or lack thereof of these models when you go to city scale is really informative. One of the things that we get asked a lot that we don't always talk about on the show is how we come up with some of the ideas for challenges. Sometimes they're a little more opportunistic in terms of being able to get access to a great data set. In this case with SAR, something we thought a lot about for years. In other cases, it is a long sought technical challenges, right? And one that underpins not just SpaceNet 6, but a lot of our other projects is how do we eventually graduate from an applied research setting to something where people can start to experiment with, or at least maybe use some of our data sets or some of our findings to then do their own experiments. And I think SAR plays a critical role in that. And I'm particularly interested to see what we produce in the coming months, albeit whether it's real positive finding or simply highlighting a lot more work needs to be done. And Daniel, kind of over to you. What are you thinking about in terms of future work that you want to do? Because I know, you built a lot of foundational infrastructure with building out that baseline. So what do you have coming up in the next couple of months?
Yeah, so a couple of things. One is that we're planning to do a additional release of SAR data. So this will be a new release based on these original collects over Rotterdam that will include some new products. And the one that we're especially excited about is the inclusion of complex SAR data, meaning SAR data including the phase information, which opens up the door to a lot of different kinds of analyses, as you said, encouraging people to take this and run with it and try different things. Another thing that's coming up.
That's outstanding. And Daniel, I'm curious, we talked a little bit about that. I think it's worth just highlighting again. That's really unique in terms of putting out those types of data, like just in any resolution, but I think particularly in the resolution class that we're talking about.
Yes, that's right. This will be a pretty special data set.
All right, and I cut you off. What else do you have in mind?
The other thing that we are working on, or another thing that we're working on, let me start that over. Something else that we're working on is we are developing a library of tools for pre-processing. That is the work of preparing a data set to be used for geospatial deep learning. This will be included in an upcoming release of Solaris, our geospatial deep learning Python library, and it will include tools to support various manipulations of imagery and labels, but in particular, it will include a selection of algorithms for preparing SAR data. So that should be especially useful for data sets such as this one. This pre-processing library is built on a Python module that we're working on called pipe segments, which allows for taking small building blocks of prepared code and assembling them into more complicated workflows to do more complicated data processing tasks.
No, that's outstanding. And when we release that, based upon some real popular feedback we've had, we'll be putting out virtual tutorials on that, as well as all of the appropriate updates to our web pages and GitHub repos. So stay tuned for that. Daniel, a little teaser. I think when we release that, that merits its own podcast episode, in my opinion.
I think so.
Outstanding. And we'd be remiss in talking about SAR and future work if we also didn't mention our t-shirts. I think the overwhelming demand for our SAR Week shirts, which we used to kick off the whole SpaceNet 6 challenge. I think by popular demand, we'll be doing an additional reprint of those. So stay tuned for that as well. All right, so
we really need to open up a web store, I think, Ryan, to start selling to the audience. I think it could be a great habit.
I'm all in on that idea. If we get asked about it on more than one occasion, and I think between the shirts and some of the stickers, it would be fun. And so, if for all you listening, if you want that, write in. Let us know you want that, and we can hopefully get that up and running on the SpaceNet site. We'll count that as an aspirational goal.
Yes.
Outstanding. Well, to kind of conclude here, for any of you listening who have followed our whole SpaceNet challenge process, what we're doing right now, which is after a challenge concludes and doing the detailed analysis of the data set and code, is really, we would argue, some of the most exciting work that we're doing. And we'll be putting out a lot more material in the next couple of weeks, providing that analyses. Jake, Daniel, why don't you walk us through some other things you're thinking about doing, whether it be some blogs or other material? We've already hit on some of this a little bit.
Yeah, I mean, the 2 points I really laid out in talking about the colorization and moving towards the real foundational mapping at scale. Both of those are going to be standalone blogs, so they'll be coming out hopefully within the next 2 to 4 weeks. So watch the downlink for those. Also, we already had our first blog breaking down the winner's solutions and how the algorithm succeeded with buildings of different size, buildings of different height, and how they compared to optical data. So I would encourage everybody to check that out. With that, I'll turn it over to Daniel.
Yeah, I would just echo the point to keep one's eyes on the blog in the coming weeks, as we'll have more analysis, more data, and more software.
That's great. I think one of the other things that we didn't really talk about here, but it's worth bringing up as we're highlighting different content we're putting out there, is for the first time, a SpaceNet challenge was tied to a specific workshop at a conference. In this case, a computer vision pattern recognition, or CVPR 2020's Earth Vision workshop, featured the SpaceNet 6 challenge. And you can also find our recordings from that workshop, as well as the recordings from 2 of the contestants, or the top 5, on their solutions and why they did what they did on our SpaceNet.ai page. So we highly encourage you to check that out and look at those recordings. With that, I would say I'd like to thank, as always, Jake and Daniel for coming on the show and for making this long-sought goal of having a multimodal data set challenge come to reality. So big thanks to you. Certainly a big thanks to all of our SpaceNet partners, particularly those that put together, made this data set possible, so Capella Space and Maxar. And guys, look forward to your future releases. Great work.
Yeah, thanks, Ryan. And do we want to tease SpaceNet 7 now? I feel like this might be an opportunity to talk about that.
Here's an important question, Jake, before we get into that. Can the internet traffic, essentially, can the Apple's podcast app handle that type of internet traffic?
Boy, that's a brave question. I think we're going to test that.
All right, let's risk it. Let's risk it. Let's just see what happens. All right. So Jake, you're opening up, right? As one SpaceNet challenge closes, another one begins. And we're specifically really excited to already have announced a little teaser for SpaceNet 7, which we're looking to plan for a planned launch in early autumn of this year. And backed by popular demand, the first trifecta challenge manager, the Grand Meister of computer vision himself, one, the only Adam Van Etten will be back to steer the ship. And Jake, what are we going to do? What's happening? Is it going to be a novel data set, or is it going to be trite and boring?
Yeah, I think this is a very novel data set. So thanks to our new partner with SpaceNet Planet, they're giving us 100 different locations with dense time stacks of imagery. So the challenge is going to be focused on time series analysis and extracting how urban environments change over time. We're going to be bringing in a new metric. I think it's going to be really exciting. I know Adam's stoked. He's got the three-peat now. He's just 3 away from that Tom Brady, Michael Jordan level. I know he's excited about that. I'm happy just to have one. I do think we should start making rings to commemorate challenge management for the SpaceNet and get that championship ring.
Ooh, yeah, I'm in on that.
Yeah. So I know Adam's stoked. We're all stoked to see how state-of-the-art computer vision handles these time series approaches with satellite imagery.
Yeah, and in all seriousness, we at the opening of this episode, we talked about how we've long sought a multimodal data set. Another long sought goal for us, and this is something that goes back once again to our early days in 2015 and 16, has been a deep time series data set. There's a lot of promise with those types of data, but how they're used in a machine learning workflow, once again, a lot of open-ended questions. And we're hoping that just like SpaceNet 6 is with SAR, hopefully SpaceNet 7 could serve as a foundational data set and algorithm repository for future work. So stay tuned, as we'll be putting out our first overview of that challenge, as well as a first look at the data set in the coming months on all of our normal channels. And we'll certainly be having a podcast episode on that once we have all the challenge specifics laid out. So stay tuned. Well, with that, everyone, as always, thank you. Make sure to check out everything on the SpaceNet.ai page or the Cosmic.org page, CosmicWorks.org page. And until our next episode, take care.
Bye all.